All right, I think we get started. Welcome everyone to this week's Autonomy Talk. This week is a pleasure to have with us Professor Zachary Sunberg, who is an assistant professor in the N and HJ's Med Aerospace Engineering Sciences Department. And there is the director of the Autonomous Decision and Control Lab. So something about Zachary. Zachary obtained a bachelor's and master's degrees in aerospace engineering from Texas A&M. And then moved to California, where he got a PhD in aeronautics and astronautics at Stanford, working in the Stanford Intelligent Systems Lab. Also, before joining the University of Colorado, he was a postdoc at the University of California, Berkeley, working in the Hybrid Systems Lab. His research is focused on safe and efficient operation of autonomous vehicles and systems in different contexts, on the ground, in the air, and in space. So I guess at all levels. And a particular emphasis is put on handling uncertainty using partially observable Markov decision processes and games. And today's talk is exactly about this. The title is Breaking the Curse of Dimensionalities in POMDPs with Sampling Based on Line Planning. I'm very excited to hear more about the subject, and to the audience, feel free to use the chat during the talk to ask questions, and I will make sure to monitor that. So without further ado, Zach, go ahead. The stage is yours.
Cool. Well, yeah, thanks for the introduction, and I'm excited to be here and give you a little bit of a talk on POMDPs. So just real quick, a little bit about my lab. So this is the Autonomous Decision and Control Lab at the University of Colorado Boulder. And we try to make contributions kind of, well, we already talked about on every level of the of robotic applications, but we also try to make some contributions at every level of kind of the knowledge stack for autonomy. So we try to make theoretical contributions, like just proving theorems, which I'll talk a little bit about today. We also try to, make new algorithms that are efficient based on this theory. And then we have a bunch of different applications, which you can see a few pictures there. Unfortunately, I'll only be able to cover a few of those. So my team is on the right here. We have a postdoc, Ofer Dagan, and then currently 6 PhD students, and we'll be welcoming a couple more in the fall. So to kind of frame the talk today, I've got 2 examples for you. So the first one is one that we've probably all thought about a little bit, autonomous driving. And this is a video, it's from 2018 now, so it's getting a bit old, but you have this autonomous Waymo car that's trying to get on the freeway. And it's being really diligent and safe and putting its blinker on and trying to move over here into the left lane or into the main lanes of the freeway from the exit. But as you can see, even though it was trying pretty hard, it didn't make it in. It wasn't able to merge properly, and so it had to get off on the next exit. And so although the car was safe, it wasn't efficient in the sense that it didn't accomplish its goal in a timely manner. And so no one's going to, if we have autonomy that's safe but not efficient, no one's going to actually want to use this autonomy. So we kind of have to balance both of those. So that's kind of the first framing example I've got for you. The second one seems quite different. And so this is video from one of my colleagues, Eric Frew here at CU Boulder. And this is video of a tornado forming. So you can see they're in kind of a thunderstorm, and you can see this tornado is forming. I think they're in probably Nebraska, maybe. And so you might ask, why are my aerospace engineering colleagues out watching these tornadoes form? So it turns out that they're actually trying to study these. This is a launch of an aircraft that they send up into these storms to gather data about how these tornadoes form. And you can see a video of it flying here. So it's, flying through the storm. It's got a bunch of sensors on it trying to gather data so that they can, meteorologists can predict these storms. And the goal is to go from a warning of a few minutes that you can give people to take shelter to, 15 minutes or a half hour of prediction by looking at these storms closely. So in order to do this, you have to decide, what is the most important part of this tornado-bearing storm to fly in. And up until this point, my colleagues Eric and Brian Argro here have pretty much done this manually. They've talked to meteorologists and decided what the best place to fly is. Now, that doesn't take a lot of important things into account. For example, it's much harder or more dangerous to get to certain places in the storm. And then once you're up there, it may be easy to go, for instance, downwind, but it's very difficult to go upwind. And so that's where I'm coming in. I'm starting to work with them on ways to plan autonomously how to navigate through this storm in a way that allows us to predict what's going to happen, how the storm is going to evolve, and whether there will be tornadoes. And we also have another strategy, which are these little balloons that you can see right here that the aircraft can actually drop. We call these pseudo-Lagrangian drifters, and they're basically little balloons that the aircraft can deploy, and they flow along with the storm, giving us both information about where the winds are blowing and also about the temperature and pressure. And so the ultimate dream is that we would be able to just hit a button, have a computer calculate where to go in this storm. The aircraft takes off, it drops some of these drifters, and then is able to predict whether there's going to be a tornado and give people plenty of warning so that they can get ready. So these two examples, may at first seem quite different, but really they have a lot in common. So both are these sequential decision-making problems with uncertainty. And the uncertainty, maybe seems quite different at the beginning. In driving, the primary uncertainty is what are the other drivers going to do? Are they going to let me in safely if I'm trying to merge? And in the tornado forecasting example, the main uncertainty is what is going on in the storm. But it turns out that both of these can be modeled as what's called a POMDP, partially observable Markov decision process, which I will assume that a lot of the audience has heard of, but maybe hasn't. Maybe I'll go over a few of the details. But the challenge in both of these cases is that this POMDP has an extremely large state and observation space. So in the driving case, you need to keep track of what all of the other vehicles around you are thinking or what their dispositions are, what they're going to do. And in the storm case, you have this extremely high dimensional process that is this weather process. So both of them have very large state and observation spaces. So I'm going to talk to you about how we solve these problems with POMDPs. And even though they're very big, theoretically intractable problems, how we can solve them practically. So the talk will have 5 parts if I get to all of them. The first is kind of the promise and the curse of POMDPs, what makes them so powerful and what makes them so difficult. Then I'll talk about mathematically, how can we actually break this curse? The curse that I'm talking about is called the curse of dimensionality. And then 3 will go into, based on this theory, what kind of practical algorithms we can get out of it. In 4, we'll talk about additional challenges that come with having multiple decision-making agents interacting. And then 5, if I have time, we'll talk about our open source software for this. So part 1 is the promise and curse of POMDPs. So I have taught a lot of classes and done a lot of research on different types of uncertainty. I like to categorize it into 4 types. So the first type is aleatory uncertainty. Aleatory means that you can't learn anything more about the randomness of a process by observing it more. So an example of this is a coin flip. You know that the coin has a 50% chance of heads and 50% chance of tails no matter what. No matter how many times you observe this coin flip, that's always going to say the same, and you can't predict any better by observing it more what's going to happen. So in a sequential decision-making context, we would use a mathematical structure called a Markov decision process to model this. Another type of uncertainty is epistemic uncertainty. So with epistemic uncertainty, by observing outcomes, you can learn more about the underlying properties of the process and predict it better in the future. So for example, if you have a weighted die, but you don't know how it's weighted, by observing the outcomes of that die, you can learn how it's weighted and eventually predict better what's going to happen. And in a sequential decision-making context, we would use reinforcement learning techniques to deal with this. So as reinforcement learning interacts with the environment, it learns something about the uncertainty and is able to predict and plan better for it. Now, the blue box says static in it, and so I group these things into different categories, because this first category is static uncertainty, by which I mean that the unknown properties don't change over time. And then the green box represents epistemic dynamic uncertainty. So this is where you can learn something about the outcomes, but the states that you don't know about or that you're learning about can also change over time. So an example of this might be blackjack, where you have a deck that the dealer is dealing from that changes over time. And if you can predict what cards are in that deck, then you can actually do a lot better. And so this is modeled by a partially observable Markov decision process, and the uncertainty is in the states. And then the last type of uncertainty is interaction uncertainty, which is modeled by a game. So if you have chess, for instance, there's actually no uncertainty in the state of the system or the rules of the system, the dynamics of the system. The only uncertainty is in what your opponent is trying to do. And so this results in a lot of interesting mathematical things that we'll get into at the end of this talk if we have time. So to model these different types of uncertainty, we have different versions of Markov decision processes. So Markov decision process, for the purposes of this talk, is going to be defined by the state space, which is a set of possible states the system can be in, and transition probability distributions. That basically is a distribution of the next state given the current state in action, an action space, and then a reward function. And the state space here can be a discrete set of states, like in this diagram on the left, where we have states 1, 2, and 3. And we have different transition probabilities given that we take action B, for example, in states 3. We have 70% chance of transitioning back to state 3 and a 30% chance of transitioning to state 2 and getting a -10 reward here. Now, the state space could also be a continuous state space. So like if you're doing satellite navigation, for instance, it might be a 6-dimensional continuous state space. So we're going to deal with both discrete state spaces, continuous state spaces, and hybrid state spaces. So like I said, this can, in the transition probability distributions, this formulation can deal with aleatory uncertainty. So one of the problems, if you've ever dealt with these MDPs, is what's called the curse of dimensionality. So you can solve these MDPs relatively easily with algorithms such as value iteration. The problem is if you have a multiple dimensional state space, then this quickly results in a large number of states that make it difficult to solve. So let's say we have a kind of one-dimensional state space here that we've discretized into 5 elements. The size of the state space is 5 here. This could represent like where you are longitudinally on a road or something. If we upgrade to multiple dimensions, so 2 dimensions, so we basically have like an X coordinate and a Y coordinate in each space, then we discretize it into 5 cells for each dimension. Then we have 25 states. If we go up to 3 dimensions, we get 125 states. And basically, the number of states, if we discretize this, grows exponentially with the dimensionality of our state space. And so this is called the curse of dimensionality. So the next kind of paradigm that we'll talk about is reinforcement learning. So in reinforcement learning, we assume that we don't know the transition probability distribution exactly, and we may not know the reward function exactly. And so this allows us to handle the epistemic static uncertainty. And a lot of reinforcement learning techniques are able to bypass this, to some extent bypass this curse of dimensionality, because they use neural networks to approximate the functions that we need to approximate over this large state space. Now, if we go to the partially observable Markov decision process, then we assume that instead of getting to observe the state of the system, we actually only observe observations from an observation space that are generated with an observation probability distribution. So we're not sure exactly what state the environment is in. And this allows us to represent dynamic epistemic uncertainty by using some uncertainty in what the state of the environment is. So let's look at an example of what a POMDP might be. So this is a simple classic toy example that we talk about sometimes. It's called the light-dark problem. The idea here is that we have a state space that's discrete. It's the set of integers. That's on the y-axis here. And then we have some time step on the x-axis. And the goal is to take some specific action. We'll say that the actions are these 5 numbers, -10, -1, 0, 1, and 10. And the goal is to take action 0 at state 0. So we get 100 reward if we take action 0 at state 0, and we get a -100 reward if we take action 0 at some state that's not 0, and then we get -1 reward, otherwise just to incentivize it to get to this special action quickly. The trick is, so you want to go to this 0 state and take the 0 action. The trick is that you only get accurate observations in a specific part of the state space. So this light region, and you can see that with the definition of the observation distribution. So the observations are real numbers, and they're normally distributed with a variance that decreases as we get closer to 10, and it's actually 0 here at 10. So we get accurate observations up in this region. So if we initially don't know what state we're at, then we need to take this policy where we go to the light region, we localize, we learn exactly what state we're at, and then we take actions to get down to a = 0 so that we can confidently take that action 0 at state 0 without getting the negative penalty for taking it in the wrong place. So this is a kind of a representative example of a POMDP where we have these competing goals of gaining information by localizing and then actually getting the reward by going to state 0. So compared to MDPs, POMDPs are much more difficult to solve. And I'll try to illustrate why with this picture. So in an MDP, we have an environment that has some state here, and we would read the state from this environment, and then we would execute a policy or run an online planner to find the optimal action to take. In a POMDP, we don't get a perfect observation of the state. So for instance, the state could be 7, and we might get an observation of -0.21. So we don't want to it's not optimal in a POMDP to make decisions based on only the current observation. We really want to take into account the entire history of actions and observations that we've taken before. So we can, in the light-dark problem, for instance, we can remember when we were near state 10, and then take the actions necessary based on that in order to get the reward at the goal. So this is difficult because we have to now find a policy based on the entire history of actions and observations. One way to kind of get around this or simplify it, which is more kind of matches more how humans make decisions, is to use a belief updater. So humans typically don't think of I'm going to make a decision based on all of the individual observations that I've received in the past. They typically use these observations to form a belief about what the state of the world is. And so the belief is a distribution over the current state given the history, all of the actions and observations. And it turns out that you can make optimal decisions based only on this conditional belief distribution. And you can also use Bayes' rule to incrementally update this belief based on the previous belief and then the previous action and the current observation. The problem is this belief update, even when you have a discrete state, is order of s squared. So if your state space is large, then due to the curse of dimensionality in MDPs in the state space, then you can have a very expensive belief update. Moreover, this POMDP is essentially like an MDP on the belief space. So the curse of dimensionality in POMDPs is somewhat worse than it is in MDPs. So the idea behind this is that we can take the original state action transition and reward function from this POMDP, and we can convert it to an equivalent MDP with a new state action transition and reward function, where this new state space that we're planning over is actually the set of all possible distributions over S. So this is the set of possible beliefs. The problem with this is that even if we're in a discrete state space, as we add this possible state to our belief, each new state in our POMDP results in a new continuous state dimension in the belief space. So this results in we're planning in a belief MDP where the space that we're planning over now is continuous with one dimension for each discrete state. And so you can imagine in realistic problems where the underlying state space is continuous, it's even more difficult here. So this suggests that these problems are going to be extremely difficult to solve. We might wonder whether there's a theoretical guarantee or theoretical kind of bound on how difficult there is, and it turns out that there is. So this paper from 1987 proves that for even discrete POMDPs, even if the process is stationary and the planning horizon is restricted to be smaller than the state space, these POMDPs are p-space hard problems. This paper is really convenient for presentations because you can just take screenshots, and the first line of the proof, if you just cut off the screenshot, shows exactly how the proof works, which is they just reduce the QSAT problem to POMDP, and that proves that it's p-space hard. So we have we have a very strong theoretical reason to believe that this problem is very hard. So what are we going to do about that? That's the curse of POMDPs. How are we going to break this curse? So you might think that these things are kind of hopeless. Like, why do we even think about solving POMDPs if they're so difficult? Let me offer you some hope. And so the first kind of ray of hope that I'm going to give you is in a simpler process than solving an MDP or a POMDP, which is just simply integration. So let's say that we want to integrate a function. We want to find the expectation of some function f of the state according to a belief distribution. So an expectation is an integral. That's why I relate this back to integration. One way to do this, find this expectation if we discretize the state space, is to just take the definition of the expectation over a discrete state space, which is taking the value of the function at each state, multiplying it by the belief probability, and then adding those up. The problem is this is subject to the curse of dimensionality, since we have to sum over all of the states in this space. But there is a way around this, and this is called Monte Carlo integration. So the idea with Monte Carlo integration is that we sample a bunch of states, SI, from this belief distribution, and then we estimate the expectation with this estimator Q sub n, where we just evaluate the function for every one of these states, add that up, and divide by n. Everybody has probably done this at some point before. Now, what we want is some idea of how accurate this Qn is. And one measure of that is the variance. So if we take the variance, take the definition of the variance, and expand this out using a few identities, we get that the variance is equal to the variance of this function f of si, of these sampled i's, which you can estimate empirically, divided by the number of samples in that you get. And we can actually use some concentration bounds to get a guarantee that the probability of the difference between this estimator Qn and the estimated value of this expectation, the probability of that being greater than some epsilon, is equal to the variance of this function over n times epsilon squared. Now, the remarkable thing about this is that this guarantee has no dependence on the size of the state space like it did before. So this variance decreases based on the number of samples that you have, and it doesn't depend at all on the dimensionality of the space here. So this is great news, right? It means that there are some algorithms that rely on randomization that can estimate something that are not dependent on or not subject to the curse of dimensionality. So we have one ray of hope here. But integration is a lot simpler of a process than solving an MDP. It turns out, however, that similar ideas do apply. So one way to solve an MDP is to change it into a tree search problem. So basically, we take this MDP here, we unroll it into a tree where each branch is either an action or a state. And we can take these, if we want to solve for the best action at 3, we can take this tree and calculate what the rewards are in each branch, back those up using dynamic programming, and then calculate the value of taking A and the value of taking B at state number 3. Now, constructing this full tree is very computationally inefficient. It's exponential in the depth, because every time you branch here, you get many more states and actions that you have to expand. But it turns out that we can use an algorithm called sparse sampling to limit the number of nodes that we have to expand. So in sparse sampling, we start out at a state node, we expand for all actions. In this drawing here, we just have 2 possible actions. And then, so the naive way to do this would be to expand for all of the states in the state space. So we have a new state node for each state in the system. Now, if the state space is large, then we're going to get this exponential dependence that's the size of the state space raised to the depth of this tree. So it's going to be heavily dependent on the size of the state space, and hence subject to the curse of dimensionality. Now, what sparse sampling does is it says, well, what if we don't really need to consider all of the possible states. Let's limit this to some fixed number, C. In this case, in this drawing, it's 3. It usually has to be a lot more than that. So what happens if we only consider a fixed number of randomly sampled states rather than the full possible state space? It turns out that this was analyzed in a 2002 paper. And it turns out that we get this very nice theorem, which is a little bit hard to read, but the result is extremely nice. So if we use this sparse sampling algorithm, the running time depends only on R max, the maximum reward, gamma, the discount factor, and the epsilon that we want to achieve for our accuracy. And it does not depend at all on the size of the state space, right? Because we only sample C states at every point in the tree instead of the whole state space. And it turns out that this algorithm is provably near optimal. So the value, this is the expected sum of accumulated rewards for this algorithm A minus the difference from the optimal value is less than or equal to some epsilon. So we can achieve a boundedly suboptimal policy without any computational dependence on the size of the state space. So this shows that we can actually escape the curse of dimensionality for MDPs. That's great. That's a great sign for POMDPs too, because like I said, a POMDP is an MDP on the belief space. So we should be able to just apply this to POMDPs, right? So one idea would just be to apply this to a history MDP. So where we solve a POMDP by just using the history as the state for a new MDP. Turns out that we can't do this easily because we can't simulate the next history based on the previous history. So we don't have a way to get the next state in the history MDP. The other thing that we might try to do is just apply this sparse sampling technique to a belief MDP. Turns out that this doesn't work either, or at least it's not cursive dimensionality free because each belief update depends on the size of the state space squared. So there's not a straightforward way to apply this to POMDPs. What we can do, however, is use an approximation, another approximation, which is particle filtering. So the idea that we're going to pursue here is that we want to approximate this POMDP as a particle belief MDP. And then we'll solve this particle belief MDP to make a decision in the original POMDP. So a particle belief approximates a belief with a set of sampled states, SI, and the belief is equal to a Dirac delta function times a weight here. And we basically represent each belief with a collection of either unweighted particles or weighted particles. And in order to update the belief, we sample from the transition probabilities. So we update each of these particles, sampling from the transition probabilities, and then we weight them based on the observation likelihood from the observation we received. And that allows us to keep track of this particle belief. So maybe if we can approximate the POMDP with these particle beliefs, we can have a cursive dimensionality free algorithm for POMDPs. Before I go on, I want to be clear that we made some assumptions for this analysis, but these assumptions are not very restrictive. So we considered continuous state and observation spaces and discrete action spaces. So the state and observation spaces are basically one problem. The action space is a different problem that I won't talk about too much. We also assumed some regularity on the observation probability distributions. In particular, we said that there's no Dirac delta observation densities, or the observation density can't be too peaky, essentially. And then we also said that there's bounded reward, and we think that a lot of these can be relaxed to some extent. We also said that there's bounded reward, that we have a generative model for the transitions, which means that you can sample from them, but you may not be able to evaluate the density. And then we have an explicit model, which means we can evaluate the density for the observation distribution Z. We also proved this for finite horizon, and we restricted the beliefs that you can prove this over, basically beliefs that you can reach from the initial belief, just to avoid getting caught up in these edge cases of really strange beliefs. So those are the assumptions. If you don't understand those in detail, it's okay. But if you're a POMDP guru, these might be important for you. Okay, so in order to start proving that this particle approximation is a good approximation for the POMDP, we first needed to prove this divergence concentration, or this concentration inequality for these particle approximate beliefs. So one thing that we need to do this is to estimate, to use importance sampling, essentially. So we're going to estimate an expectation with respect to some distribution P, but we're only going to be allowed to sample from Q. So in a POMDP setting, P is the distribution of states not conditioned on the history, and P is the distribution of states conditioned on the history. Q is the distribution of states not conditioned on the history. So in order to do this concentration inequality, we need some measure of how different the sampling distribution Q is from the true distribution P. So we use what's called the infinite Renier divergence. This is the essential supremum of the probability of under P over the probability under Q. So a low Renier divergence would look like this. High Renier divergence would have a high peak compared to this Q. And then theorem 1 says that if P and Q have a bounded Renier divergence, then the expectation of this function minus the estimate of it is less than some lambda. And that lambda depends on both n and this Renier divergence. So that's our convergence kind of theorem for seeing how far these beliefs are away from the true belief. So again, the idea that we want to prove here is that this belief MDP, each of these kind of orange shapes represents a true belief, a distribution over the states, is close to this particle belief MDP, where these beliefs are represented by particles. Now, one of the difficulties here is that they're with a continuous observation space, there's a continuum of possible branches in this POMDP tree. And so in order to prove that these are close to each other, we need an intermediate tool, which is going to be this algorithm called sparse sampling omega. The omega just looks like a W for weights. So sparse sampling omega, the algorithm looks like this. Essentially, what it's doing is taking a particle belief at the root node, running it through all of the actions, and then sparsely sampling the next observation and getting these resulting beliefs here. So essentially, the structure of this proof is that belief MDPs are close to this sparse sampling omega, and particle belief MDPs are also close to the sparse sampling omega, meaning that these two things are close together. So the first thing we want to prove is that the sparse sampling omega is close to the particle belief MDP. This is going to be an inductive proof. I won't really go through the induction, but I'll show you at each step, we want to prove that the error going from this level of the tree to the next level of the tree is bounded. So the first error is basically the immediate reward, and then the second term of this error is the error in the future value. And this future value has two components. One is due to the Monte Carlo transition approximation error, and one is due to the induction error. So basically, the first term is due to that we're sampling these states. The second term is due to that we're sampling these observation branches. And then the second part of the proof is proving that the belief MDP is close to the sparse sampling omega approximation. So this now has two terms. This B term that has to do with the value now has four terms here. Basically, it has a term due to the importance sampling error, which is the weights of these particles compared to the true belief, the Monte Carlo approximation error, which is just due to we're approximating these through sampling. And then the inductive function approximation error, which means that we're sampling these transitions. And so with both of these kind of steps between sparse sampling and particle belief MDP, and then sparse sampling and true belief MDP, we can actually get a bridge that bridges between this belief MDP and the particle belief MDP. And this was proved by one of my students that I co-advised with, Claire Tomlin, Michael Lim here. And the remarkable thing about this proof is that for any epsilon and delta greater than 0, we can choose a number of particles, C, that's high enough so that the Q value estimates for the belief MDP that represents the POMDP exactly, and the particle belief MDP that approximates the particle MDP is less than or equal to epsilon with probability 1 minus delta. And this relationship has no dependence on the size of the state space or the observation space. So we can free ourselves from this curse of dimensionality. And we get to finally this final theorem, which I'm not going to read for you, but it says that the distance between the true optimal value at some belief is it's within epsilon of this approximated optimal value within epsilon with high probability. Now, you might be a little skeptical at this point because you're saying, I'm giving you a free lunch. We have this PSPACE hard problem, and you're saying that it's not actually that hard. So for the actual guarantees here, the number of particles for any realistic problem is going to be too high for any direct safety guarantees. But as I'll show you in the next few slides, in practice, this works extremely well for improving efficiency. All right, so that's the proof that we can get around analytically, mathematically, we can get around this curse of dimensionality. Now I'm going to show you how this translates into practical algorithms. So basically what this does is if we have any MDP algorithm, such as sparse UCT or Monte Carlo tree search, or tree search with double progressive widening, we can take this from an MDP problem and apply it to a POMDP by using this particle belief approximation. And so this is very powerful. We can basically bound the error that we're going to have, and it doesn't depend on the size of the state and observation space. So one algorithm that kind of uses this principle is called POMDPs. We actually created this algorithm before we had any guarantees, just kind of based on a hunch about this, and tried to prove the guarantees later. But this algorithm essentially works for this reason. And so this is a very efficient algorithm for doing online planning in POMDPs. So let's go back to our examples. So autonomous driving. So I said that autonomous driving depends on predicting what the other road users are going to use, are going to do. The challenge with this is that we have some external states that we can measure, like the position, velocity, turn signals, all that stuff. And then we have some internal states about that describe what the other drivers are thinking. So their intentions, dispositions, distraction, maybe focus. And I said we could formulate this as a POMDP. I'll go into a little more details about this. So the state space for this lane changing POMDP is the physical position of the X, Y, and Z, X and Y locations. So the X is the lane-wise location, Y is the between the lanes location of the ego vehicle and all of the other cars. And then we also have the internal states of the other cars, which is represented by this theta. Observation is just the external physical states of all the other cars. And then our action space is discretized. And the reward function is a positive reward if we're in the goal lane, and then a negative reward for any hard braking actions or any actions of our vehicle or any other vehicles going too slow or taking hard brake actions. Now, you might object, this reward function doesn't include crashes. Well, we took care of that by using an action shield, because we never want to even consider actions that could result in crashes. And we have a kind of a hard braking action that's always available to prevent crashes. So we have this kind of proxy safety that penalizes hard brakes and going too slow. So the actual planning looks like this. You can see kind of we're constructing this tree. Each of the red, so the color of each of the other cars, the green car is the car that we're controlling. The color of the other cars represents how aggressive they are. Red cars are aggressive, blue cars are timid, but we don't know that as when we're planning. So we have all of these different predictions, which are these red and blue lines, conditioned on how timid or aggressive the other cars might be. And then the white lines are the trajectories that we're considering. So you can see as we're planning and gaining physical observations about the other cars, we get better and better at estimating what their internal states are. And so we have more accurate predictions about what they're going to do. And this allows us to eventually make it. The goal here is to make it to the left lane before X reaches 1,000. And as you can see, we're able to just barely do that. So we're able to, by estimating the internal states of the other vehicles with this POMDP framework, we're able to do this. Now, this is a very large POMDP. There's, for each vehicle, the internal state is 10-dimensional, and there's up to 10 other vehicles on the road at a time. So this is a 100-dimensional continuous POMDP. Actually, I should say the internal states are 7-dimensional and the external states are 4-dimensional. So this is like a 100-dimensional continuous POMDP, a very large state space. There's no way you could solve this without the theory that this particle approximation theory that I just went through. So that's maybe a cool video. The question is, does this result in better performance on average? Well, we compared this in terms of safety on the x-axis and efficiency, the fraction of simulations that were successful on the y-axis. And we used two MDP-based alternatives. And so these have kind of a Pareto curve that by adjusting the reward function, we can show how this trades off. And then we have an upper bound, which is represented by omniscience over the internal states of the other drivers. So if we knew exactly the states of the other drivers, this is the safety and efficiency trade-off that we could achieve. So the question is, can the POMDP approach close this gap between these MDP lower bounds and the omniscient upper bounds? Turns out that this POMC-POW algorithm, based on this theory, can indeed close that gap. All right, so let's look at the second example, which we haven't flown yet, but we're developing kind of the algorithms, and we're going to fly this next year. So in tornado prediction, the internal states or the hidden states are a little different. Instead of being the internal states of other people on the road, they're actually the states of the storm. So our tree looks something like this, where we have the blue, green, and red represent kind of different forecasts of what the storm could do. And then we have actions that represent when we can either drop our drifters or where we're going to go. So you can think of the state as the physical state of the aircraft, and then the question of which of these forecasts represents the true state of the storm. So you can see here kind of a representation of different storm states and how the planning trees will work out in each of these different storms. The action is, where do we fly and when do we deploy our drifters? And then the reward, there's different reward functions that you could use. One interesting one is a terminal reward, where you have to make a prediction about whether there's a tornado, and you get a positive reward if you get that prediction correct, and a negative reward if you don't. So that depends on narrowing down which of these forecasts is close to the truth, and whether the forecast close to the truth include a tornado in the future. So we've solved this on some kind of synthetic data. This, which you probably can't see, is a wind field. It's just kind of the direction that the wind is growing. And each of our different forecasts have a different wind field. And then they also have kind of anomalies. This is showing the anomalies in some temperature data from some synthetic data. So there's these little regions that have more differences between the different forecasts in the storm. And so our question is, can the POMDP planner plan to these regions that are different? Also based on the wind conditions and whether we can actually make it to these places. So here's an example trajectory that we planned. In this case, there's these three regions that have interesting deviations between the different forecasts. These deviations over here actually have higher magnitude, but it's impossible for the vehicle to reach them because the wind is blowing the other way. And so it shows that you can actually, the planner is able to reason about both the wind and the differences in these and go to this place where it's able to, based on the measurements that it takes, distinguish within these forecasts and forecast a tornado well. And these results just show that our planner is this blue here, and to the right is a higher confidence on the true forecast. So we're able to do much better than some of these baselines here. Okay, I'm about out of time, but I'll quickly go through a few other ways that we've applied this. So a classic one is this autonomous driving. This was a paper from, I think, 2015, where they put some autonomy on a golf cart, and they used a POMDP to basically navigate amidst these pedestrians. Now, this was in a time when we didn't have these particle belief approximations. So the dimensionality of the state and observation space that POMDP planners could solve was very limited. So they had to kind of destructure the problem where the actual path that they were going on was determined by a path planner, and the speed along that path was determined by a POMDP planner. So with our new particle belief approximations, we can actually do both the path planning and the speed planning at once, and you'll see that we're able to reach the goal much faster. Another application is drone search and rescue, where we're working actually with an organization called the Boulder Emergency Squad to do kind of this operator-centric planning for sending a drone out to search an area for a lost person. The operator kind of puts in some information about the environment, and then we have our POMDP planner that actually plans an efficient path to look for it. And we're testing this out with actual emergency operators right now. We've also integrated some learned components. So for instance, if we have a high dimensional observation space like images, we might want to use a neural network to process those. We've demonstrated ways to integrate those components, and we kind of use this online planning as a backbone. And then we also think that there's some advantage in explainability. So because we're using online planning rather than a neural network, we kind of have the data with us for every decision that we make. So we are hoping that we can explain things better. All right, in the last couple of minutes, I'll talk about some challenges with can we apply this theory to multiple agents? So in a POMDP, we assume that there's only one agent making a decision. In a partially observable Markov game, we assume that there's multiple agents making decisions on partial information. And both of the agents may have aligned goals or opposing goals, and they're all trying to decide what's best for them to do based on this partial information. So if you're familiar with these types of problems, you have to do a lot of reasoning about what the other players are thinking, right? If you used a POMDP approach for everyone, everybody would have to be thinking about everybody else's belief, which is, kind of the subject of this this scene from Princess Bride, where they kind of reason about what each other are thinking. So this is a very difficult problem. And instead of an optimization problem, where there's an optimal answer or we can compare these, this is a game, so we now have Nash equilibria, and we might have mixed Nash equilibria. So this is an open question still that we're trying to address. Are there state size and observation size independent algorithms for partially observable Markov games? So if you've read Russell and Norvig, you might recognize this figure. This is a figure for an algorithm designed to solve incomplete information extensive form games. This is a small version of poker, actually. And in poker, you have to reason about what the beliefs of the other players are, and you might even bluff in order to do that. So instead of beliefs in these types of games, we have information states that group possible states together without assigning a probability weight to them. And this allows you to reason about things like bluffing. The question is, can we do this with POMDPs, because there's this difference between these information sets and weights? We've actually just started working on an algorithm where we group weighted particle beliefs together into information sets. And we believe that this is the key to being able to do this. We have some initial results where we have a POMDP planner SARSUP, and then we have a counterfactual regret player in a high dimensional tag game here, and we're able to produce much less exploitable strategies with essentially this algorithm. All right, well, it looks like I'm a bit out of time, so I'll have to skip our open source software. We have some cool open source software. It's called POMDPs.jl. But I will end here. Hopefully I've given you some hope that even though POMDPs have this curse of dimensionality, that we can find good practical algorithms based on particle approximations and solve them efficiently. So thanks for your time, and I can take any questions.
Thank you very much, Zach, for the great talk. Let's open the stage for questions. So you can either type in the chat or raise your hand and ask directly. and I will try to monitor the two. So let's first start by a question that was typed in the chat by Subrata, which was, how do you factor near-miss incidents in your POMDP algorithms?
Yeah, that's a good question. So, and I would say so there's kind of this trade-off, right, between safety and efficiency. And so these sampling-based algorithms are not good at safety guarantees. You essentially have to have something else to do safety guarantees. So like for this autonomous driving case, we actually had a shield that eliminated actions that could result in a like actual crash. And so, like you said, there's what we're now thinking about are these near miss incidents. So there's these hard braking incidents are essentially near misses. And so the idea is that we do occasionally sample near miss incidents, and they do have these they do have a negative reward. And our theory says that on average, if this bad incident is if this this very bad incident is likely enough and bad enough, you will sample it enough to avoid it. And that's essentially what our theory will get at, is that some events are very unlikely, some events are very bad, and on average we will sample enough of those, and that fortunately does not depend on the size of the state or observation space. So I guess we don't specifically do anything to deal with near misses, but our theory says that they will be sampled enough, the actual hits will be sampled enough to essentially avoid these near misses. I don't know if that helps, but that's kind of the answer.
Thank you, Zach. Any other question for Zach? Oh yeah, Colin, go ahead.
Yes. Hi there. Thank you again for the talk. I guess I had a quick question about when you have additional sources of epistemic uncertainty in the POMDP framework. For example, if you don't have a generative or explicit model of the probabilities of an observation given an underlying state, could you then be able to combine some of the more reinforcement learning approaches alongside these particle filters and sparse sampling spaces in order to kind of build a representation online of the probability of an observation given a belief?
Yeah, so I'll say there's two kind of aspects of that. One is that you can always, well, yeah, so one thing to note is that a POMDP is actually extremely optimistic in the sense that we assume, like you said, like you kind of got at, you assume that you at least can sample from all of these probability distributions. So your question is, what do we do if we can't sample from them? So one thing that you could do is kind of just come up with a conservative probability distribution and put some of this uncertainty back into the state. So for instance, if you have kind of like a prior of what the probability distributions could be, then you can actually include in the state what are the true probability distributions. So then your state includes both, I guess, the physical state and kind of, actually, I don't know what slide I'm trying to go to. I don't have a slide on this. You could include maybe in the state space the probability distributions themselves. So that's one thing you can do. The other thing you can do is learn models for these offline. So let me actually go back to this slide. So if you want to do it efficiently online, you kind of have to have at some level a prior distribution over what your distribution could be. And you can learn that online by throwing it into the state. You can also learn, if you have a bunch of data, you can learn, for instance, these transition probabilities or observation densities from data offline and combine them together online with tree search. And we found that in this study, this paper, we found that to be really successful. It really cut down on the training time to learn these aspects of it independently and then combine them online with the tree search.
Great, thanks.
Thank you,
I'll
Colin,
read
for
that
the
paper.
question. Any other question for Zach? I guess I had a question related to, so you were a bit rushed at the end, but I'm curious to hear about how do you think your results for the non-game case extends to the game theoretic case?
Yeah, well, I mean, essentially what we're saying is with this theorem, wow, really highlighted everything here. So with this theorem, we're saying that the values, okay, one way to solve a partially observable Markov game would be to create a huge matrix game where each action on the matrix game is, I don't know if you guys can see me talking, but I'm talking with my hands. A huge matrix game where each action for each player is a different policy. And in the hard part about that, there's two hard parts about that. One is that the number of possible policies you have is extremely large, exponential, and a bunch of different things. And then the second one is, how do you estimate the values to put into that game matrix for each of these policies? Well, this theorem right here says the Q values the Q values are close together when you use this sampling approximation. So if we can prove that essentially the Q values for each of these different policies in this matrix game are the value functions for those different policies are close together, then you can solve that matrix game and you know that you get something, there's ways to bound how far away from a Nash equilibrium you are. So essentially we're saying every entry in that matrix game is, if we use enough particles, it's going to have a close enough bound. Now, those are not going to be practical guarantees at all, because the number of particles you need is going to be so big, and the number of possible strategies is going to be so big. But it will probably at least say that that bound does not depend on the size of the state space and observation space. So maybe we don't need to worry so much about how big the state space and observation space is. And then we just evaluate it practically.
Yeah, that's actually very interesting. So I guess you can, another statement could be that if you can characterize well the interaction patterns of the different players, that might even simplify further the, so not only it doesn't depend on the state, but you can also make the state lighter in some sense. But
yeah, definitely. Like if you add some kind of graph structure, that exactly. Yeah, that, I mean, that could definitely cut down on things. So, but we're just we're starting out trying to prove this base case, and then I'm sure there will be many years of papers written on how to make that better.
That's very good. Yeah, thank you. So there is another question from Troy on the chat, who says a paper titled "Recurrent Model-Free RL Can Be a Strong Baseline for Many POMDPs," ICML 2022. And this paper re-examines using recurrent model-free RL to realize POMDPs. As such, what are the advantages and disadvantages of using online POMDPs planners versus such learned planners for POMDP?
Oh man, this is like such a great question. And I think they're really complementary approaches. So in order, for all of these problems that I showed, we have some offline thing that helps us. So for this, for the driving problem, for instance, we just have a heuristic policy that we use for rollouts. And for the tornado stuff, actually, we have a simpler heuristic policy. So we mostly use heuristic policies. But in reality, you're going to have to learn something and combine the online and offline planning in something similar to AlphaGo. So AlphaGo had like a policy network and a value network that helped in this tree search, and then it used tree search also to plan online. So you're going to have to do some combination of this learning, and reinforcement learning is going to allow you to store knowledge from a bunch of pre-computed things in an efficient to access way. Now, what are the advantages of online planning? I think the biggest advantage is composability. So one nice thing about this paper is that we were able to learn like an observation density and a transition density offline, and then combine them online with online planning. So if you're talking about end-to-end reinforcement learning, you have to learn all of that together in one shot and get all of that knowledge together. And so you could train on a wide variety of environments, et cetera, and try to make a policy that can handle all of those environments. But what if something shows up that was not in your training environment, or if somebody else trained a model for that new environment and you want to integrate it with your already trained models? So if that's not in your training data, you either have to retrain or do some fine tuning or something. If you're using RL, if you're using this online planning, you can actually compose all of those individual models for different environments and stuff in this very kind of clean way. And you can use this idea of particle beliefs as kind of a framework for composition. And we showed in this paper that works really well. Like, we cut down on the offline training time because we were not trying to do complete end-to-end learning, but we were training individual modules and putting them together in this online planning. And I also think, so these LSTMs, I don't think that they'll be, so the belief updates are not the hard part about POMDP RL. We have good approximations for those, especially, for instance, particle filters. And so we should, instead of training an LSTM to learn how to do the belief updates and make decisions at the same time, I think it'll be much more scalable to integrate reinforcement learning with these kind of belief updates that we know how to do really well already.
Thank you,
I think that online planning can be a really useful complement to reinforcement learning.
Nice, thank you. And thank you, Troy, for the question. It seems that this was a very good, somehow state-of-the-art review question. Very nice. All right, it doesn't seem we have more questions. I think you left your coordinates in case people want to reach out for deeper ones.
Yeah, absolutely. You can go to cuadcl.org and find, I'll put the URL up at the end. And didn't get to this stuff. And find all of this information and contact me.
Thank you very much, Zach. And so thank you again for the talk, and I wish you good luck for the next steps.
Yeah, thank you very much.
And thank you all for participating. See you all next week for the next talk. Bye-bye.
Yeah.